this video, we're going to integrate this integral you see here, 1 over x squared minus 9 to the 3/2 power. And we're going to do this by trigonometric substitution. So first we need to identify which identity we want. Because of the form, we're going to use secant squared minus 1 is equal to the tangent squared of the angle theta. So the main features of the Pythagorean identities here is that they always involve the number 1. Because we're working with the number 9, we need to factor to change this into a 1. And so we're going to factor the 9 out of our denominator, and we end up with x squared over 9 minus 1, all multiplied by 9, and then raised to the 3/2 power. We'll be able to pull this 9 out of the 3/2 power later, but from where it stands right now, it's not going to affect using the identity. So we need x squared over 9 to replace the secant squared of theta. And so if I take this and I solve it for x, I can get x squared is 9 times the secant squared of theta, and so I get my value for x that I want to use. X is 3 times the secant of theta. If this is my x, then my dx is going to be 3 times the secant of theta times the tangent of theta, d theta. So now I can start plugging these into my original integral and see if I end up with an integral I can actually work with. I'll have the integral. Dx is going to be replaced by 3 secant of theta, tangent of theta, d theta. Inside the 3/2 power, I will still have this 9, and then x squared over 9 is the same as secant squared minus 1. And it's all raised to the 3/2 power. And this is where we use the identity. Secant squared minus 1 is the same as tangent squared. And so we can replace it, and then we'll be able to take the actual radical, the square root, that's part of the 3/2 power. So I have the integral of 3 secant theta, tangent of theta, d theta. In my denominator, I'm going to have 9 times tangent squared of theta, all raised to the 3/2 power. Tangent squared to the 3/2 will be tangent to the 3rd power. 9 to the 3/2 is going to be the square root of 9, which is 3, to the 3rd power, which is 27. And so I'm working with 3 secant theta, tangent theta, d theta, divided by 27 tangent to the 3rd power. So now simplifying my terms, I end up with a 1/9 and a secant theta divided by a tangent squared theta. There are a couple of different ways we can approach this integral. There are some tricks we can use, but probably the easiest way that I found to do this is to switch things into sines and cosines and see if we can find an easy substitution. And so we write this as 1/9, the integral of 1 over cosine, divided by sine squared over cosine squared, all with respect to theta. And then we reduce this complex fraction, and we end up with the 9th, the integral of cosine of theta divided by sine squared of theta, d theta. When it's written like this, the substitution u equals sine of theta will work very nicely. And so when we do that and then perform the integral, we end up with negative 1/9 times 1 over u, or negative 1/9 times 1 over sine of theta plus c. The last step is to take this and rewrite it in terms of the original variable x. So if I draw the triangle based on the substitution that I worked with, if this is the angle theta, then the original substitution was the secant of theta was x over 3. I can use this information to label sides of my right triangle and then use the Pythagorean theorem to find the other side. So I'll get x and 3 as my 2 sides, and then the square root of x squared minus 9 as my 3rd side. And so if I want to find out what 1 over sine of theta is, I can do this. just from the sides of the triangle. This is going to give me negative a ninth. Sine of theta will be the square root of x squared minus 9 over x, so 1 over it will be the reciprocal, x over the square root of x squared minus 9, plus the constant c.